Hello, we are Team 5, and I'm Hyun-Suk Jung. Today we introduce MUSE multimodal utility for story enhancement. This is the outline of our presentation. In today's presentation, after a brief recap of our motivation, we'll explain the final network for our works and our results. So, in the modern society, storytelling is more than just a means of telling stories. It's used as a means of creative expressions, learning tools, and psychological healings. However, there are many limitations in the current storytelling process. It costs a lot, or there are the cases where users cannot properly use a text for storytelling. So we aim to make this stage less burdensome by using MUSE, the multimodal interactive story generator, which inputs the multimodalities and generates the story interactively.
Hello, I'm also E, and I will introduce about the end-to-end integration of our project in this. This slide provides an overview of a view system, and initially user input the audio and image or text. Then the backend process perform audio emotion analysis and image analysis on the input data and extract context for the story generation. Subsequently, using the Llama model to generate the text-based story, the generated story is delivered to the user, and also if we need, the summarize for the use of a context in the future story generation. Finally, the input chat and generated story records are managed and visualized. The entire process ensures the seamlessly for the user experience. The MUSE project employed the various AI models to handle the different type of input format. For audio, emotion analysis is conducted to use and to provide the mood of the story from the audio input. For imaging, the Lava model is used for image analysis to extract the key character, action, and locations. This helps in understanding the context of the image and constructing the scene of the story. Based on the collected context, the Llama language model generates the story. The generated story is then summarized for use as a context in future story generation. This entire process allows for creation of a consistent story based on the user input.
Okay, thank you, Kosu. Now I'll be going over the Lava model. It's more specifically on the prompt used to generate the tokens for the main story generation model. Yeah, so this is the main role of what the Lava model does. Given a system prompt, the image to text model generates important details about the image, such as the subject, location, and the action of the main subject. These details are later used as important tokens to the main Llama generation prompt, which will influence the generated story's flow and the main events. As such, the Lava model's output structure is important, as it must provide enough detail and description in a consistent manner to produce a seamless interactive story. And this is why the Lava system prompt is investigated in depth. So considering how the LLM prompt is structured, we first try to focus on obtaining short keyword-based outputs. In other words, given an image, we tried extracting just the subject, location, and action in the length of a single token. And to do that, we use the following prompt, which highlights brevity of the answer that we expected, and especially given the fact that the prompt was in the form filling base. This, in fact, results in a very short descriptions of images as shown in the examples. And after some consideration, however, we figured that such extraction of information cannot take full benefit of multimodality. Images are meant to hold more information than words, and to do that, we believe that the Lava model should be as descriptive as possible, answering the questions specific to appearance, color, and what kind of action it does with using more adjectives and adverbs. So now aiming to get more descriptive information from images to maximize the descriptive nature of multimodality, the prompt has been changed to the following. With the use of the terms descriptive, describe, we expected the model to provide more details about the main subject in the image. And as shown in the examples, however, while there was more detail, it was not enough, and some images seem to generate less or more information than the other. And as I mentioned before, we want consistency in the details from any arbitrary image. So also, apart from the goal that we initially wanted, due to the nature of the term describe, the model seemed to output full sentences, which cannot be directly used for our LLM prompt. So we finally decided to change the format entirely. While we used the form-filling based prompt, we decided to modify the prompt such that the model knows what we're looking for more specifically. Furthermore, starting the portion of where the model's answer goes in, we made sure the image-to-text model generates descriptions starting with the keywords themselves. The output can be seen in the next slide. With the final prompt, we've tried different images with differing number of subjects in the main image. So starting off with no human subjects, the model generates more descriptive details that start with the keywords themselves, following up with more adjectives and adverbs. Images with one human subject, the details do not stop with the subject's appearance and outfit, but extends to describing the background that is even blurred out. And it considers the main subject's context, in this case, a baseball player, and links the blurred image to a baseball field crowd, and even adding running from base to base to the last action statement. And now when we add one more subject, the model successfully provides in-depth descriptions about the subject. But as you can see, sometimes the model seems to merge two characters into one. And however, this is a trivial problem as the main goal of the image provision is to add more detail, contextual detail, rather than changing the contextual flow, which can already be done using text inputs. And the last example with multiple main subjects, it also shows a lot of detail that starts with the keywords themselves. Okay, so this is apart from the lava prompt engineering, Hansup and I have already fine-tuned the audio sentiment analysis model by adding new sentiment class. So given an input, the model extracts the features to classify the song into one of the 5 categories: happy, sad, aggressive, dramatic, and romantic. And the emotion class is then used as a token to the prompt for the story generation, as shown in red. As aforementioned, the baseline model originally had 5 emotions. We believe that this does not cover the entire emotion wheel and decided to add angry and tender as emotion classes. This is done by using Google's AudioSet dataset, which is a collection of 10-second sound clips drawn from YouTube videos. The dataset file containing the dataset has the YouTube video ID, the start time, end time, and the labels. The label for angry and tender were specified in the dataset, and with the YouTube to MP3 API, we downloaded the sound clips within the specified timeframe. Using MFCC spectrogram and other audio-based features, we trained the dataset, and now Hansup will now explain the output.
So these are the training results of the baseline model and 6 emotion model adding angry and 7 emotions model adding tender. When only angry was added, the performance was almost similar to the baseline, but when the tender was additionally added to the 7 emotions, the accuracy dropped significantly. Additionally, when tender was added, there was a rapid change in accuracy during the training process. I could reason this as follows. First, about the low accuracy, since the source of the dataset is different, the Google and the Librosa, the similar music can refer to the different class. Specifically, among the added tender emotion data in Google dataset, there are many sounds similar to happy music in baseline Librosa dataset, which makes wrong choices. Second, about the rapidly increasing accuracy for the 7 emotions model, I could reason that as the tender music, which is clearly different from the baseline happy music inputs to the training process, the model starts to select tender, enhancing its accuracy rapidly. So I selected the 6 emotions model which has similar accuracy to the baseline model. So let's look at how emotion affects story creation. First, for the following boxing, photo, and text input, James play baseball. If no music is included, a story is created as follows. We can see that there are a few phrases that express emotions even though we don't input sounds. For instance, in the third paragraph, his eyes look into his opponent's appears determination burning within them. This is because we use lava to describe the image, not detect the image, which includes some emotional descriptions of objects and actions. And now this is the story generated by the model when angry music is added to the same inputs. So phrases expressing angry emotions such as the crowd cheering and the error with anger or vicious counterattack or with a fierce cry appear quite often. In this way, when the sound emotion, the sound similar to the image and text context, like between the boxing and angry, we can see that the MUSE has the tendency to further emphasize the emotions. Now, this is a story generated by the model when the romance music is added to the same input. The word romance is explicitly mentioned in the story, such as a fear, a sense of excitement, and romance. In this way, when emotions somewhat conflict with the story expected from images and text or previously storyline, like between the boxing and the romance, we can see that the MUSE has a tendency to explicitly mention those emotions to indicate the mood. So now, this is the story generated by the model when the sad music is added to the same input. In keeping with the sad mood, the story focuses on falling at boxing rather than playing on boxing. In this way, we confirm that the MUSE can change the plot of the story easily depending on the emotions in the sound, even though the emotions has nothing related to the text or images.
Okay, Unge and I have also worked on the Llama prompt engineering, and we'll first give a brief overview of our old design. So this was what we had originally planned. By using the system prompt for the story generator, we planned on using the tokens extracted from the multimodal models. These are then fed into another prompt specifically used for the LangChain summarizer. These are then fed, and once LangChain summarizes the story up to now, it feeds its summarized output of about 2 to 3 sentences to both the summarizer prompt and the new context history so far. So this is the initial prompt that we have used for the story generator. We first assign LLM a role, telling it that it is a storytelling assistant. We further emphasize that we want the story only, as it tends to digress and add some interactive cues. We then use some rules that the LLM should follow, emphasizing the coherence, tone, language, and interactiveness of the output it should produce. And finally, we entice the model to generate the story based on the LangChain history and the new input that the multimodal models have generated. This prompt, however, has shown several problems that we call findings, and Ungi will go through each of these and demonstrate what we have found and finally decided to use our final prompt.
So after trying a couple of example story generations, we came to the conclusion that the original prompt was too long and complex. Like most LLMs, the number of output tokens are usually fixed when inference is requested. However, the number of output tokens also includes the tokens in the input prompt. And this is done so that the model does not end up forgetting the input prompt. However, this means that as contextual information, for example, the summary, gets longer, the effective output story gets shorter. Due to the nature of LLMs, it is very hard to control the input prompt's length, since the summary and the visual context is an output from another LLM. As a consequence of having a long input prompt, is that the LLM cannot incorporate all provided context properly into the story within the given output token length, and ends up getting cut off. For example, here's one of the outputs we encountered according to the inputs shown on the left. You can see that the visual information about boxing and the character James provided in the text input are reflected properly. However, there's only a slight hint of sadness, which is the input song, towards the end of the output. Looking at the flow of the story, the LLM would have been able to develop this emotion further if it was allowed to generate more tokens. Finally, the context about James going to class is completely lost and nowhere to be seen. Now, recall that the original prompt was quite complex, as it assigned a role to the model and also gave it specific rules to follow. This was originally in the prompt as a means to control how the output is given to us. However, it ended up actually confusing the model even more, and as a result, it sometimes acted more like a generic chat model instead of a story generator. As shown in the example below, the output starts with, here's a story based on the details, which is clearly not what we want as part of the output. Next, we found an issue using LangChain Summarizer. The Summarizer mixin class, which is one of the underlying classes used for summarization, had a hard-coded context structure. If you gave an input and the LLM produced a corresponding output, the input to the Summarizer LLM will always be in the following form, with human and AI, indicating a conversational environment. As a result, the produced summary becomes similar to the previous example shown, where unnecessary comments are included. Finally, we found a major issue relating to the compatibility of Llama 3 and LangChain in general. Llama 3 uses the following end of sequence token in order to indicate to itself to stop the autoregressive generation process. However, running Llama 3 through LangChain results in a failure to produce the correct end of sequence token. This happened even after we explicitly tried to change the end of sequence token to the correct string. As a result, Llama 3's generation goes past what should have been the end and starts breaking down, generating useless text. In the example below, we see that after the generation is complete, the model is unable to stop itself and ends up generating Python code, which we never asked for. So due to this incompatibility, we had to resort to creating our own generation and summarization pipeline without LangChain, using the basic Hugging Face functions. As with before, the generation prompt is used as input to the story generation. After the story is generated, the output is looped back and placed in a summarizer prompt. This is fed into Llama 3 again, along with previous summaries, to create a new summary, which is used for further iterations. The main difference is the removal of LangChain such that Llama 3 can function properly. Furthermore, the generation prompt has been simplified due to the previously mentioned issues. Initially, we briefly state the role of the LLM. Next, the prompt, which has simple instructions, is dynamically structured depending on the existence of certain types of inputs. We chose a dynamic prompt approach since without it, if an input was not given, then the preceding string, for example, subject, action, location, will still exist in the prompt, but with nothing following it. This can end up confusing the LLM. Also, the structure in which we provide the context are more explicit in order to remove unneeded words and provide clear information to the LLM. The summarizer prompt is much simpler. We ask the LLM to summarize the given story. Then, we combine the previous summary and new output story together to form an entire story. We re-emphasize the task and entice it to output just the summary without any comments. Okay, now I will tell you about what kinds of things we consider during GUI implementation. Our GUI implementation using streaming and user can easily input the audio or images and text chat. It supports the real-time interaction and provide immediate feedback and visually display the generating stories with streaming. Additionally, the responsive design ensures the consistent usability across the various platforms such as the smartphone, tablet, or desktop web application. This design is similar to recently chat platform like ChatGPT or CloverX, so that we can offering a similar familiar environment for users. Lastly, I will explain the enhancement of responsiveness through the asynchronous process. Asynchronous process reduces the user waiting time, so it can enable real-time updates and interaction. So our process of story summarization are provided with asynchronously. So so we can keep this interface as the responsiveness. Additionally, generated stories are provided through the token streaming offered immediate feedback. So asynchronous process story summarization process while the user typing. So it can make appear if there are no delay. So this asynchronous process needs the user experience and maintaining the real-time interactions.
So let's see our use demo. So we're having a feature. This is the track bringing from the side decided to go to the city and transfer image and sound as follows. It will generate the stories as follows. You can see that like the phrase, the bright lights and giant rainbows overlaying him, but he had a sense of freedom. He was struck by the sheer number of people rushing to and from. You displaying the image for Times Square. Also, like a phrase gains the sense of belonging, like he had finally found his place in the world. The crowd around him share a clap, and James felt a sense of joy. The sound input fluently changed emotions.
Second iteration, the story dynamically translates insert or promotion and discover opportunities. So first, part of promotion or next is as the present here, highlight the model can create the comparing paper. So this is showcase the integration of the image input along the model to generate the vivid and engaging examples that mirror the city's energetic atmosphere as we input in previous story.
Also, when we introduce the sequential test, please notice that often occurs sensitivity, knowing some agony and pain and audio. So generate the story as follows. Instead of watching boxing with Simon like before, the focus is now the person who repeats. Now, the person who got lost and matching the mood of the music. Like the phrase the change spirit of is done by the intensity of spike, red smile, and clapping on the back. Muse makes the story with the full on gloomy emotions in the song. So let's look at our survey results. We evaluate our model using a survey with a scores out of 5. First, to evaluate interactivity, the main component for our works, we investigated interactivity, continuity, control, and intent components while generating the story using MUSE. And we also evaluated the quality of stories, which is essential to the story generation model and also related to the multimodalities. We registered the question regarding logicality, interestingness, creativity, and reactivity for multimodalities that the story generated. And the rating was divided into an evaluation for the user's experience and an evaluation for the example story containing a series of well-established input and creation flows. And for the multimodalities like images or sounds, the results were good. It had a high average rating. In contrast, there are some complaints about story context, especially the low ratings for flow control during story creation show the need for improvement to maintain and reflect the previous context. And besides them, there were many useful comments left by users. So I felt that it didn't capture the mood of K-pop songs very well. We can see that we need to improve the audio models to be more generally. Actually, there was some very harsh rating regarding music, indicating that our current audio model needs to be more general and fine-grained. Also, there seems to be a jump in the flow of the story for each iteration. It can be seen that our context model needs to be improved to better reflect the context of the story. In addition to this, we felt that additional support such as the regeneration or flexing the input modalities were needed to improve usability.
And so based on the additional survey comments and our own self-evaluations, we have come up with several ways that could improve our model further. Firstly, our current model can only classify 6 different emotions from music. This means that fine-grained control over the mood is not possible. With training on more classes or using a descriptive audio captioning model specialized to our needs, can vastly improve the quality of the context extracted. For example, instead of just extracting sad from the song, we could be able to extract a calm, melancholic atmosphere that develops into a strong depressive emotion. Such descriptions could also include developments of the mood over time and need not be limited to music, but also ambient sound, for example. Next, the retainment of context could be improved. Currently, our summarizer outputs around 120 tokens for the summary before the end of sequence. And this short output means that there's aggressive summarization where details can get lost. A potential improvement could be to periodically checkpoint these summaries and then build a system to manage them. Performing these checkpoints can help mitigate the information lost throughout iterations. Currently, after generating a story, the summary of it is stored and given, and the given story cannot be modified. And if you allow modification, such as modifying each different input, then we can allow more fine-grained control to the users. And lastly, as a usability improvement, we can allow different media files to be inputted through URLs. And this is our overall role distribution. And that's it. Thank you for listening.